Continuation of environmental science topic. Today we are going to learn about material balance. So material balance is applied in various fields and industries. We will be having a quick recap, nothing else. A very basic idea. Okay. So chemical engineering, material balance is crucial in designing and optimizing chemical processes such as chemical reactions, distillation columns, and extraction systems. Environmental science, it is used to track the movement and transformation of pollutants and nutrients in natural systems like water bodies and soil. Food and pharmaceutical industries. Material balance is applied to ensure product quality and process efficiency in food and drug manufacturing. Energy protection. In energy systems, material balance is used to analyze fuel combustion, emissions, and energy conversion processes. Then waste management. Material balance helps assess waste generation, treatment, and disposal strategies. In conclusion, material balance is a fundamental concept that ensures the conservation of mass within closed systems. It is a versatile tool used in various fields to analyze and optimize processes, track the movement of substances, and make informed decisions about system behavior and efficiency. A deep understanding of material balance is essential. Then meteorological parameters, pressure, temperature, precipitation rate, wind, etc. Meteorological parameters are crucial measurements in the field of meteorology and climatology. These parameters help scientists and researchers understand and predict weather patterns, climate trends, and atmospheric behavior. Here we will discuss 4 key meteorological parameters like pressure, temperature, precipitation, and wind losses. So pressure, atmospheric pressure, often referred to as air pressure, is the force exerted by the weight of the air above a given point on Earth's surface. It is typically measured in units like millibars or inches of mercury. Measurement parameters are instruments used to measure atmospheric pressure. High pressure systems are associated with stable, clear weather, while low pressure systems often bring clouds and precipitation. Then variation. Atmospheric pressure varies with altitude. It decreases with increasing altitude. Standard atmospheric pressure at sea level is about like this, 103.25 millibars. Temperature is a measurement of the kinetic energy of molecules in a substance. In this case, air. It affects various weather phenomena and climate patterns. Then measurement. Thermometers are used to measure temperature, often in units such as degree Celsius or degree Fahrenheit. Then diurnal variation. Temperature typically exhibits diurnal variation, rising during the day and falling at night. The highest daily temperature occurs in the early to late afternoon. Then seasonal variation. Temperature also varies seasonally due to the tilt of the Earth's axis, resulting in summer and winter seasons. Then precipitation. Precipitation refers to any form of water, liquid or solid, that falls from the atmosphere to the Earth's surface. This includes rain, snow, sleet, and hail. Measurement. Precipitation is measured using rain gauges or snow gauges depending on the type of precipitation. The unit of measurement is typically in millimeters, of inches. Then a distribution. Precipitation varies greatly by location and climate. Some areas experience frequent and heavy precipitation, while others are arid with minimal rainfall. Then wind roses. Definition. Wind roses are graphical representations that display the frequency and strength of wind directions at a specific location over a certain period, often a year. They provide valuable information for various applications, including urban planning and climate studies. Components. A typical wind rose consists of a circular diagram divided into segments, each representing a cardinal or intercardinal direction. The length of each segment indicates the frequency or intensity of wind form in that direction. Once again, I'm going to read this one. Wind roses are graphical representations that display the frequency and the strength of wind directions at a specific location over a certain period over a year. They provide valuable information for various applications, including urban planning and climate studies. Components. A typical wind rose consists of a circular diagram divided into segments, each representing a cardinal or intercardinal direction: north, northeast, east, southeast, south, southwest, west, northwest, like that. So the length of each segment indicates the frequency or intensity of wind from that direction. Wind roses are used in climatology to analyze prevailing wind patterns which can influence factors like temperature and precipitation. They are also essential in wind energy studies to determine suitable locations for wind turbines. For example, in a wind rose, a longer segment pointing to the east might indicate that easterly winds are more common, while shorter segments in other directions suggest less frequent winds from those directions. So, in summary, meteorological parameters such as pressure, temperature, precipitation, and wind direction are fundamental for understanding the predicting weather patterns and climate behavior. So, scientists and meteorologists use various instruments and tools to measure and analyze these parameters, helping us gain insights into Earth's atmospheric process. Wind roses, in particular, provide a graphical representation of wind patterns that aid in various applications from climate studies to renewable energy planning. So, candidates preparing for this need to have a clear understanding of these topics. Humidity mixing ratio, saturation mixing ratio. Humidity mixing ratio and saturation mixing ratio. Humidity is a critical meteorological parameter that characterizes the amount of moisture or water vapor present in the air. It is essential for understanding weather patterns, cloud formation, and the likelihood of precipitation. In addition to humidity, meteorologists often use two related concepts, mixing ratio and saturation mixing ratio. Humidity definition: humidity refers to the amount of water vapor present in the atmosphere. It can be expressed in various ways, including relative humidity, specific humidity, and absolute humidity. What is relative humidity, or RH? Relative humidity is perhaps the most commonly used measure of humidity. It is expressed as a percentage and represents the ratio of the amount of water vapor in the air to the maximum amount of air can hold at a given temperature and pressure. High RH indicates air near saturation, while low RH suggests drier conditions. Then specific humidity. Specific humidity is the mass of water vapor per unit mass of air. It is often used in meteorology to describe the actual amount of moisture in the atmosphere and is expressed in grams of water vapor per kilogram of air. Then absolute humidity. Absolute humidity is the mass of water vapor in a given volume of air, typically expressed in grams per cubic meter. It represents the density of water vapor in the air. And mixing ratio. Mixing ratio is a measure of the mass of water vapor present in the air compared to the mass of dry air. It is expressed in grams of water vapor per kilogram of dry air. Unlike relative humidity, mixing ratio is not dependent on temperature and pressure changes. Then calculation. To calculate the mixing ratio, you divide the mass of water vapor by the mass of dry air in a given volume. It is a straightforward measure of moisture content and is commonly used in weather forecasting and meteorological analysis. So, application: mixing ratio is particularly useful for assessing the moisture content in the atmosphere, especially in situations where temperature and pressure may vary, such as an upper atmosphere. Then saturation mixing ratio. Definition: the saturation mixing ratio, also known as the equilibrium mixing ratio, represents the maximum amount of water vapor that air can hold at a specific temperature and pressure without condensation occurring. It varies its temperature and is lower at colder temperatures. Relationship with relative humidity. And the actual mixing ratio equals the saturation mixing ratio at a particular temperature. The relative humidity is 100%, indicating that the air is saturated, and further cooling or moisture addition will lead to condensation, cloud formation, or precipitation. Its application: meteorologists use the concept of saturation mixing ratio to assess the potential for cloud formation and precipitation. When air particles cool to the point where they reach saturation, clouds can form and precipitation may occur. So, in summary, humidity mixing ratio and saturation mixing ratio are crucial concepts in meteorology for understanding the moisture content of the atmosphere. Relative humidity measures the amount of moisture relative to the maximum possible at a given temperature and pressure, while mixing ratio provides an absolute measure of water vapor content. So, saturation mixing ratio is the maximum amount of moisture air can hold without condensation. These parameters are essential for weather forecasting, cloud formation analysis, and understanding atmospheric moisture dynamics. And radiation and wind velocity, adiabatic lapse rate, environmental lapse. Radiation in meteorology refers to the transfer of energy through electromagnetic waves. In the context of weather and climate, there are two main types of radiation: solar radiation, That means insolation. Solar radiation or insolation is the energy emitted by the sun in the form of electromagnetic waves. This energy reaches the Earth's surface and drives various atmospheric and surface processes. Impact. Solar radiation is the primary source of energy for Earth's climate system. It influences temperature, weather patterns, and the Earth's energy balance. Solar radiation is responsible for heating the Earth's surface, leading to the development of high and low pressure systems and driving atmospheric circulation patterns. So, terrestrial, also called infrared radiation, is the heat energy emitted by the Earth's surface and low atmosphere as a result of their temperature. So, terrestrial radiation is a key component of the Earth's energy balance. It is emitted continuously both day and night and helps cool the planet. So, greenhouse gases in the atmosphere, such as carbon dioxide and water vapor, absorb and re-emit some of this infrared radiation, contributing to the greenhouse effect and maintaining Earth's temperature. Then, wind velocity. Wind velocity, or simply wind speed, is the measurement of how fast air is moving horizontally. It is typically measured in units like meters per second or kilometers per hour. Wind direction, the compass direction from which the wind is coming, is also essential to characterize wind patterns fully. So, impact. Wind velocity is a critical meteorological parameter that influences weather patterns, climate, and various human activities. It is a key driver of weather phenomena such as high and low pressure systems, storms, and wind-related hazards like hurricanes and tornadoes. So, wind energy is harnessed for power generation through wind turbines. Then, adiabatic lapse rate. The adiabatic lapse rate is a measure of how the temperature of a parcel of air changes as it rises or descends in the atmosphere without exchanging heat with its surroundings. There are two types of adiabatic lapse rates: dry adiabatic lapse rate or DALR. The dry adiabatic lapse rate represent the rate at which the temperature of a dry air parcel changes as it rises or descends in the atmosphere. The standard value is approximately 9.8 per 1,000 meters. Understanding the DALR is crucial for meteorologists to predict temperature changes in rising or descending air masses. It influences cloud formation as air parcels may cool to their dew point, leading to condensation and cloud development. Then, moist adiabatic lapse rate. The MALR represents the rate at which the temperature of a moist air parcel changes as it rises or descends in the atmosphere. Unlike dry air, moist air involves phase changes as water vapor condenses or evaporates. The MALR varies but is generally less than the DALR. It depends on factors like the amount of water vapor in the air. The MALR is essential for understanding cloud processes and the release of latent heat during condensation, which can influence the stability of the atmosphere and the development of precipitation. Environmental lapse rate. The environmental lapse rate or ELR is the actual rate at which air temperature changes with altitude in the Earth's atmosphere at a specific location and time. It is measured by observing temperature changes through radio sonnets, weather balloons, or atmospheric sounding instruments. The ELR is crucial for assessing atmospheric stability and determining weather conditions. And the ELR is significantly different from the DALR or MALR. It can indicate the potential for raising or sinking air to lead to cloud formation, precipitation, and weather changes. The ELR helps meteorologists make forecasts and understand temperature profiles in the atmosphere. So, in conclusion, radiation, wind velocity, adiabatic lapse rates, both dry and moist, and the environmental lapse rate are fundamental meteorological parameters used to study and predict weather and climate patterns. These parameters play a central role in shaping atmospheric processes, energy exchange, and the behavior of the Earth's atmosphere. Next topic is interaction between Earth, man, and environment. Interaction between Earth, man, and environment. The interaction between Earth, man, and the environment is a complex and dynamic relationship that has evolved over millennia. It encompasses the interplay of human activities, natural processes, and the impact on the surrounding environment. This intricate relationship has profound implications sustainably, ecology, and the well-being of both humans and planet. Later complex topics we'll be learning tomorrow. Thank you for listening.